Sian, yesterday we covered on these things, mostly on the statistical concepts. And from here. So you remember we talked about probability and all that, right?
Yeah.
So yesterday we just tried to do a linear regression on our own, a simple linear regression. So let me quickly take you through that part again. And did you get time to go through? So there was an Excel that I had shared, this one. So this is the Excel that we used yesterday.
Yeah, I saw it.
So what we did here is, okay, so first is we saw, so there are two type of machine learning problems, right? You remember, one is classification, one is regression. So classification, can you tell me which one is what? Because that is the first thing. If you don't understand what is a classification problem, then it will be a problem in near future for you. I cannot hear you clearly. There are some disturbances.
Yeah,
I
classification.
honestly, okay. So classification is something which will have a desired outcome at the end. You know what the outcome is going to be. That is classification. And regression is something, okay. Yeah, thank you. And regression is, yeah, because I could not hear you what you said. Anyway, regression is something which you have to forecast. You don't know what the outcome will be. That is regression. So if I ask you, you have to select the India team for tomorrow's match out of Virat and some other players, which one should bowl, bat first and all of that. That will be a classification problem because you know how many outcomes you have. Let's say you have 10 outcomes. Out of 10 or 11 players, you have to select one. So that outcome is fixed. You are just classifying them into individual segments. That is a classification problem. But similarly, on the other hand, if I ask you, let's say, how many scores how many runs Virat will make tomorrow, or how many wickets some other player will take, Mohammad Sami will take. So in that case, that will be a regression problem because the outcome you don't know. Outcome could be 0, 2, could be anything. That is not limited. The runs could be anything. Runs, it's not like only 0 or 1. It could be anything. So those type of problems are known as regression problem. Now, now the important thing is let's focus on regression. So on regression, what we try to do here. So this is lot of things we did. So what essentially we tried to do here is let's imagine we had two variables, height and weight, height and weight. So the first thing which we have to do is both are numerical. So either we can take height to forecast weight or we can consider weight to forecast height. Both will work. But which one we should consider? That is something we should. Okay. Sian, do you have access to these videos? There is an independent variable and there is a dependent variable. So what is that? Independent variable is whenever the variable that you want to predict, that will always be your dependent variable. That will always be your dependent variable. So how essentially it works? So model is essentially an equation. It's a mathematical equation that you have to build. That mathematical equation will act as the bridge between one or more than one variables. Now that mathematical equation can be leveraged for future prediction. That is what is happening in machine learning. As simple as that. Okay. So one simple thing is, if you take a, let's say, you have a bike. Okay, you have a bike. Now, let's say let's consider only two variables. One is servicing or petrol you have, and number two, mileage. let's say these are the two variables you have, or let's say, yeah, these details like bike, piston, engine piston, sorry, it's not bike, it's engine piston or something that we call, right? I don't know about the details. That is one variable. Then let's say there is something called ABS. I'm just some example, and this is mileage. So you will see these are whenever this is 4, the ABS is 2, then mileage is 70. Whenever this is 6, ABS is 5, the mileage is 90. So I'm just quoting some example here. So if I ask you, like, what will be the mileage if the piston is 9 and the ABS is 6, 4? What will be the mileage then? So for these kind of problems, this is a regression problem because you are predicting something which could be anything. The value outcome could be anything. So this is a regression problem, number one. Number two, you have to identify the dependent and independent variable. So what is dependent? Dependent is the variable that depends on other variables. So it will be mileage. And independent means a variable that does not depend on anything. So for our sake, let's consider only one variable at a time. Otherwise, we will get confused. Engine piston. So this piston variable will be my independent variable. So dependent or the predictor variable. We call it predictor. Okay, because that is the value we want to predict, and this is the independent variable. So based on piston value, the mileage will change. So first thing is that we have to do is first would be finding the correlation. So what is correlation? Correlation is how these two values are correlated. That means how these two are connected. How much of one is affecting others? How much of one is getting impacted by the other? That is what correlation is all about. Now in Python, there is a function which we have seen here. So this is the correlation function dot .cor. Yeah, this is the correlation. So between these two, it will tell you what is the correlation. So sales has a correlation with profit of 58. Now what is 58%, 0.58? That means there is a linear correlation. There is a linear correlation. Now, what is that? Let me just quickly give you an example. Correlation examples. So this will give you an idea. So I think this picture is better. So if the points, if the, these two variables, so if I take these two and if I put into an XY, it will take the shape of a dot, right? A scatter, like this. So if the shape looks like this, then that means there is a strong positive correlation. Then the correlation is positive. That means the value will lie between 0 to 1. So that will be a strong positive correlation. This looks like a weak positive correlation, and this looks like a strong negative correlation. So what is the difference between positive and negative correlation? Positive correlation means one value increase in X will add one value increase in Y. But negative correlation means one value increase in X will reduce the value of Y. So these two are inversely proportional. So if you remember about, proportion from mathematics, so based on whether they are positively correlated or negatively correlated, like it could be the value could be 0.96 or the value could be minus 0.96 like this. So this is strong positively correlated. This is negatively correlated between these two. Now, what I wanted to say, acha, this thing. So how now positive correlation means the engine piston, let's say the P engine piston is equal to positive. That means let's say the value will be 6.5 into mileage. That is how the relation will be. So that means one value increase of mileage will add, or it will be like this, M is equal to this into P. So that means one value increase of piston will add 6.5 times the mileage will increase. So this is positive correlation. And what is negative correlation? The negative correlation means M is equal to 6.5 divided by, that means if I increase the P value by 1, the M will reduce by 6.5 times. Right, Sian? You understood?
Yeah, I'm following.
You're following. Good. So that is what a positive and a negative correlation is all about. So the first thing in ML that we have to do is first we have to plot how the data point are aligned, how the data point looks like. Now, in statistics, in the Python, we have a straight simple thing, which is pair plot. Let me just write it down here. Okay, let me just write this code first, otherwise this will not run. This part I need to run first. If I run this, take some time. For the first time, it will take some time. From next time, it will be super fast. Yeah, pf dot the matplotlib matplotlib. These are the libraries dot pyplot as plt seaborn as sns. So once these two are called, sns dot plot sns dot plot. Sorry, this should be SNS dot pair plot of D. It will take little time. So what this will do is, so this pair plot function within Seaborn, I have passed the entire data frame. So what it will do, whatever combinations of graphs are possible between numericals and categorical variables, it will try to do. If it is in so if these are in integer, it will try to plot a scatter plot. If these are categorical, it will try to see a a count plot or other type of plots. So that is what a pair plot is all about. So that is the first thing that we should do. Yeah, great. So if we take any two variables, see there is not even a single variable, which is, yeah, this one has a good correlation. This is profit and sales. So profit and sales, we can see from the graph, this looks like a good linear correlation. So if I plot the correlation between them, I will get a good value. Sales and profit, 58%. It's not very good, but it's at least better. At least better. Other than that, I don't see visually if there are any variables which have a strong correlation between them. So only the profit and sales appear to be the one that have a good correlation between them. So how am I able to deduce to that confusion? Using a graph, which is scatter plot. Now in Python, instead of doing one at a time, I can do everything together. That is the advantage. I can do all of them together and it will give me the distribution. So that is the first thing we did. We tried to see the correlation between these two variables, and if the correlation is good, then we will take it. And once the correlation is there, then we will try to see the linear equation. Like if, let me put some other values. If 9, then 1. Let me put some random values here. 5 and then 85. Some, yeah, only this much. So if I plot this, what is the shape this is going to take? Right. This is going to take the shape of a linear distribution. So see here, what is the shape? So it's taking the shape of a straight line. It's taking the shape of a straight line. Now, exactly it's not a straight line, but more or less it's going towards that direction. Right. Now, what is the equation of a straight line? Y is equal to mx plus c. That we know, right? Cian, do you know this?
Yeah, yeah, we'll learn this in
Okay.
class.
So y is equal to mx plus c. In statistics, what we will write? We will write y is equal to beta naught plus beta 1 into x. Now, what they are? Beta naught is the intercept. If I make a straight line, then where exactly it will cut? How much distance would be from the x-axis origin? That will be your beta naught, and beta 1 is the slope, the angle it makes with the x-axis. Or beta naught would be your coefficient. Beta naught is the intercept and beta 1 will be your coefficient with the x-axis. That means if beta naught is equal to 0, that means the line will pass through x-axis. Then the equation becomes y is equal to beta 1 into x. So beta 1 is the coefficient. Beta 1 would be the coefficient of x. So if beta 1 is increased by that many times, that's how you can, your y and x will be, changing accordingly. So x is the independent variable, this one, because x has nothing to do here, but y depends on x. So y will be my predictor variable or the dependent variable. Just remember that thing very clearly. Now, one is dependent, one is independent. One is dependent, one is independent. Now, dependent will always remain one because at a time we are always going to predict what is the value of that one variable. But your independent variable could be more. What if you have more than one independent variable like we have here, ABS? ABS, let's say that's also another independent variable. Let's say the value is 6 or something like that. Now, how to, then what will happen? In that case, that will be added by one or more variable beta 2. That is how the equation will become then. So y is equal to beta naught plus beta 1 x1. X1 is the first independent variable, x2 is the second independent variable, and b1 and b2 are the coefficient for them. Coefficient, now if you know mathematics, you would know what is coefficient is the importance of that particular variable. If you put a high value of beta 1 and a low value of beta 2, that means x1 will get high priority and x2 will get low priority, and vice versa. Now, if we consider, when we considered one variable at a time, that was my simple linear regression when we considered one variable at a time. But the moment we changed into multiple variables, that became my multiple linear regression. Beta 1 x1, beta 2 x2, beta 3 x3, and so on and so forth. So that means n number of variables are there and n number of coefficients are there. So that is a multiple linear regression. So eventually what are we doing? We are predicting the value of y, which is any integer variable. So once that part is done, so essentially, see, the objective here, what we are trying to do is we are trying to create that straight line out of it. Now, if I put a straight line from here and display the equation and r square, this is how the equation and the formula will look like. So y is equal to 9 point something x plus this. So what will be the, let's imagine it has only one variable. Let's not get confused. Let's drop this one for now. Okay, so let's imagine this is my variable. So now what is the y? Y is equal to, what is the equation? 9, or I can just copy it from here. Yeah. Y is equal to this. Y is equal to 9 point something 64 plus 33.33. So this is the value of y. This is the value of y. Now, if we do the same thing here itself, will it work? We'll see. Let's say these are the actual mileage. Let's say based on the existing formula, I'm trying to do the same thing. So what will I do? These are my predicted mileage. That same mileage I'm predicting, but based on this, these are my predicted mileage. So I have to bring in that whole formula is equal to 9.6429 into this mileage plus 33.393. This will be the thing. Okay, not mileage, sorry, it will be engine piston. Yeah. This. So this is what I'm getting as per the prediction. As per my prediction, these are the results that I'm getting, which are actually good. The model, the actual value is 70. I'm predicting 72. The actual value is 90. I'm predicting 91. The actual value is 85. I'm predicting 82. And this one too exactly is matching, which is actually a good thing. So if I now calculate how much error I'm getting, actual minus prediction, these are the error I'm getting. And what is the average of all the errors? The average is this 0, which is brilliant. Now, this is all real. These are not real numbers, but in practical world, your error will not be 0. You have some errors into it. So based on multiple such, now, okay, that is one thing. Now, if I change, so what was my coefficient? 9.64. And this was my intercept. One is beta 1, one is beta 2. If I play around with this, 9.64 this variable, let's say I made this one as 10 and I made this one as 36. If I play around with this, then the values will change. So this is not right because my error is getting in a different direction. So that is how you have to play around with the intercept and slope so as to get that perfect line which will give you the minimum error. That is what the objective of a linear regression is. Now, once you are good with this one, then you will say, okay, these slope and intercept are good for any future values. No, now in future, if you have any new values, then you can straight away do that calculation. Like if tomorrow, let's say I have a piston of 15, so this into 15 plus 33.393, then I would be able to tell the predicted mileage. The predicted mileage will be 178 kilometers. So that is how a traditional machine learning. This is what a linear regression is. Now, having one variable is simple linear. If you have multiple, you have multiple linear. Now, why linear are we calling? Because essentially we are trying to create a straight line that will help us to decide if these points are falling on this line, then what is the probability that the next point will also fall on this. That's what we are all doing, right? And R square is 98. That means R square is something you can consider as accuracy if the value lies between 0 to 1. So close to 1 means it's a good. So you can say otherwise that this model has 98% accuracy, which is very good. Which is very good. Now, R square means how much of the errorness you can explain from this equation. Now, because obviously all the data points will not fall on same line, right? That is not possible practically. In a real world, having a straight line is next to impossible. Some will take a different, so we have seen the lines, right? Yeah. So imagine this one. If we try to create a straight line here, we can get the best possible line out of it. But can we plot all the lines in one line? That is not possible. All the points will never be on the same line. So that is how we have to operate. That is how we have to operate. So that is the thing. Now, one important thing here is train test split, dividing the data, because here what we have. So this is our actual data. We use the data to calculate the errors and create the model and all of that. But model is aware of this information and the model is giving very good prediction. But what if tomorrow the value is something else that the model is not aware of? In that case, the model will fail. You following me, Sian?
Yeah, I think so.
So any questions, any confusions?
No.
So what we are trying to do is based on existing data, we want to create a linkage, a relationship between the existing variables so that we can use it to create something for near future. That is the end objective. So for that, the concept we have is train test split. The concept we have is train test split. What is that? So train test split is something like df dot shell. So my data frame has 8399 rows and 18 columns. Right? Now dot columns. So here, let's say I have been asked to predict the profit. So the rest of all the variables will act as so in that case, what will happen? The rest of all the variables will act as my independent variable. And as I'm trying to predict profit, so profit will be my dependent variable or the predicted variable, because the profit is the one that I'm going to predict and rest will be all independent. Right? Okay, one simple thing I missed. I missed that one thing. Let me show it from here. So the example that we were seeing here, the example that we were just showing on the other page had engine two values, like one was engine piston and one was the mileage. So we chose piston over mileage. Why? Why not we chose the other one around? Because of the value of the coefficient. Because of the value of the coefficient. Like if we consider this here, height and weight, let's say, let's assume the example will be like height is equal to 0.65 times into weight. Let's assume this will be the equation. So 0.65 will be the beta 1 and beta naught, of course, we don't have here. So beta 1 naught is 0 here. So this is the equation where height is the independent variable and weight is something that we want to predict. But what about the other way around? That would also work. Weight is equal to how much it's coming? 1 divided by 0.65, 1.53. So weight is equal to 1.53 into height. So that would also work, right? So this would also work. So how do you choose which one to take? We can take both to predict both. If we consider height, if we want to predict height, then this is the equation I will consider. If I want to predict weight, then the below equation I will consider. So which one I will consider to use? The one, the simple answer, you just remember it, has the highest coefficient. That is the variable that we will consider. The one which has the highest variable coefficients, which is this one. This one has the highest coefficient. So weight, so 1.53 is of course more than 0.65. So because this 1.53 is more than 0.65, that means there is a high chance that height is able to explain weight compared to weight to height. Just tell me if you followed that or not. As this value is more, it means the height has more power to explain what will be the weight than the other way around, because this association is better. 1.53 is more than 0.65. This is the equation that we will consider for all our model. So that is one thing I missed in the last exam.
Okay.
Normally we know we will be given this is what we have to predict, but there could be situations where you will be just given a data set and you will be asked to do something out of it. So you don't know what to predict. So in that case, this is the technique that you will use, and you will see which coefficient is higher. That is the variable that you will choose as your dependent variable, as your prediction, right? So that is one thing that you have to do. Now coming into the interesting thing of train test split. Train test split. And these are the things, let me quickly explain. Multi-collinearity means this is a problem when you have a multiple linear regression. Now, x1 is correlated with y, that we have seen. X2 is correlated with y. These are good things. But what if x1 and x2 are correlated within themselves? That is not good thing, right? So that is something which is not good at all. So that is something which is known as a multi-collinearity problem. So if we are facing something like this, we should work on it and we should fix it. You're getting my point? So that is an issue which is known as multi-collinearity. In that case, there are two options. Either we have to drop the variable. That is the first thing. Like if x1 and x2 are correlated, we have to drop one of the variable. Otherwise, this whole multiple linear regression equation will be completely wrong. That is one thing. Else we have to drop, or we have to reduce the coefficient value, reduce the weightage or the coefficient value. So x1 and x2 are linked, so we have to reduce one of them's coefficient value. Let's say earlier the coefficient value was 1.53, I have to take it down. You getting my point, right? What I'm trying to say?
Yeah.
So that is how you tackle multi-collinearity, error distribution. So these are in details I talked yesterday, but quickly I will tell. So error distribution means how much the error is spread out. So you explain, you saw. Okay, let me just do it here. So error distribution means what? So in machine learning or statistics, we will call errors as residuals. So error distribution, we will call them as residuals. That is the term that we use. So residuals means what? Residual means once we have, like we saw right in our example. So there is actual prediction and there is a predicted prediction. There is some prediction and there is actual. Actual minus prediction is the error. How much you are getting error from the actual value. So if you plot that in a normal distribution, then if the distribution takes the shape of like this, a normally distribution graph, if you plot the errors and if it takes the shape of this, that means the errors are normally distributed, which is good thing, which is the ideal scenario. I mean, that means your model is good, right? That means your model is good if they take the shape of a normal distribution. And second is homoscedasticity. I will show that quickly here. Homoscedasticity, what is that? Homoscedasticity means the errors should be equally spread out. Okay, this is a good example. So see, the red one is homoscedastic. That means the difference between this error point and this error point on the positive and negative side, the distance is same and this remains constant. This is known as variance. This is known as variance, how much spread out they are, right? So that is homoscedastic. But that is not the case with this, which is heteroscedastic. So at some places the error is less. At some places the error is high. So this is a wrong model. So if your model gives you errors in this form, that model is not right. But if the outcome of the model errors are like this, that means yeah, it is a good thing. So you should consider that model. So these are the two things that you should consider for error distributions: normality and homoscedastic. Okay, good. Now we will consider a very interesting thing of train, test, and split. What is that? What is train, test? So how much is the shape we saw? 8399. 8399 are the rows that we have. So let's say these are my data. How many rows it has? 8399 rows. Now, if I have to make a model here, let's say this is the box where I'm making a model. So model is what? Just the equations. Y is equal to, let's say this is a multiple linear regression. So what is the model? Model is an equation. Y is equal to 1.6 into x1 plus 2.9 into x2. Like that. Let's say this is the model. This is the model. So if I apply this, so how will I deduce to this equation based on these variables? No. What I have to do is I have to split them up. So out of 8399, let's say I will take 80% of that. So how much is 80%? Is equal to 0.8 into 8399. So this much. Let's make it round. So 6719 records. Let's say out of this, what will I do here? So I will essentially split that into two halves. This is one and this is one, right? So this is one, this is one. So this is what? So this is 80% of the data and this is 20% of the data. If this is 100%, if this is my 100%, then this is 80% and this is 20%. I have done that. Why? The reason is I will create my model based on 80% of the data, which I will call as training data. I will call this data as my training data. So this 80%, which is 6719 rows, these many records I will use to calculate the coefficients 1.6, 2.9, error terms and all, or whatever we have seen until now. So that is everything will be done based on this data. And whatever is left, how much is left? 6719, 1680. So that 1680 will be my test data, testing data, whatever. So once I am good with this, then I will test whether they are giving me correct results or not based on this data. Because the model has not encountered this data. Model is based on this data, the 80% of the data. So model is not aware of this 20%. So that is the data I will use to calculate what the the real values I know, what are the real values and what are the predicted. This is what I will calculate based on the test data. And once that I have, I will calculate the errors and other error matrices I will calculate. Based on that, I will take a call how much is my accuracy and whether I should consider this model or not. You following me?
Yeah.
Any questions until now?
No, the strain test it's fine. Yeah.
So that is what the train test is happening. And this is the most important for any ML model. Now, few people go one step beyond and they create a, what they do? So few people, let me just, few people do like this. Let's ignore the numbers, otherwise it will be wrong. So sometimes we do this technique as well. We take 70% of the data for training the model, 20% for testing the model, and then again 10% of the data for validating the model. So this is probably one segment and this is another segment. That is how you can consider. So this falls under one umbrella and this is under another umbrella. This is completely unknown. The model has no idea about this data. This data is completely unknown, but this model will be trained on this and then I will use this to fine tune the model or to upgrade the model to see how much errors I'm getting. And then I will use the 10% to just to see how the model is performing. That is for the model performance, right? So just understand this. Training is for model development. Testing is for model evaluation. And this is for model performance. How the model is performing. These are the three key things of a train test split. So once this part is done, what we will do here now, we will try to see how this is happening in Python. So for that, I have to import this thing, Scikit-learn. So for the first time, it will take time. Now, what will I do from Scikit-learn dot pre-processing import and no, sorry, this is not pre-processing. One second, I'm also trying to remember what was it. This is the module. Now within there are multiple objects. So within sklearn, under model selection, we have this function train test split. So this is the function. What okay, let's go in details. We will go in details what this is doing. But understand from one line, this helps to create the train test split. This helps to create the train test split. I will just copy this segment and then we will see how it's happening here. Okay, let's comment this out first and we will come to this later. So first I need X and Y. What is X and Y? So X and Y, as I explained, so Y is equal to beta 1 x beta 1, you know, right? So X means independent. Y means dependent, right? Just always remember this thing. X is independent, Y is dependent. So I have to create my XY accordingly. So what is the model? So this is the model. I wanted to predict the profit of this is the model that I have to build. I have to predict the profit or let's say, let's predict the sales. Sales is something that we want to predict. Okay. Now for that, what I have to do, I have to select the independent variable first. So we can have one independent variable, we can have more than one independent variable. Let's take more than one for now. So let's take profit and let's say order quantity, right? So this is my x, and what is my y? Y is equal to df dot sales. So that is my x and this is my y. Or you can write it in this way as well. It's up to you. Sales, right? So these are my x and these are my y. Are you sure? Let's see. X, print of x if I do. Yes. Print of y if I do. Yes, it's coming. But instead of print, always you should try with type. So this will give you a very detailed thing of what's happening. So type of y is a pandas series because this is a one-dimensional. And for x, this will be a data frame. Brilliant. So x, y sorted. We have x and y. Now what we have to do, we have to use this formula. What is the formula? Let's try writing it here again. Let's keep the older one intact. So these are the things that we have to write. So what is x train? One is x test, one is y train, one is y test is equal to train test split. And then within this formula, I have to pass two values, x and y. One is dependent, independent test size. That means 33% I am considering for test and 67% for training. We can change it. Let's make it 2. That means 20% for test and 80% for training. And random state is a just state that we consider so that because everything is random. So every time we run the model, the things will change. Just to have that uniqueness and that constant nature in our model so that next time we run this code again, the values will not change. That is why we need a random state. Also, we need some other things. If needed, you can specify the stratify. Stratify will maintain. Now, this is not needed for regression. This will be needed for classification model, stratification. So it's not needed for now. So if I run this, yes, the code has been executed. So what is the value? Yes, xtrain dot shape gone into this. And hello, can you hear me? Hello, Sian, can you hear me?
Yeah, yeah, I can hear.
So what we are seeing here is the training and testing split is happening correctly. 80% is going into training and 20% is going into test. Now, how the data looks like is this. This is the X data and how the Y data looks like this. Only one row, just the outcome. So the train test split is done. That was an important thing that we should consider because the X train and Y train will be used to this X train and this Y train will be used to create the model. And then X test and Y test will be used to, these two will be used to verify if the model is performing well or not. Let's try that. So what we do, so from Scikit-learn, now this is the ML package that we have. So we should know what are the things that we needed. Now from Scikit-learn, we have to get this one, linear model. From scikit-learn.linear model, import what? Import linear regression. This is the function. This is the function that we need. Yes, this has been imported. Now let's create an object. Model is equal to linear regression within code. Yes, this object has been created. Now, what is inside this model? If I run only this, yeah, it has this value, linear regression inside of it. Just this model. So once this model is done, then what we have to do? We have to fit. We have to fit the values. Fit is a function which will take the inputs X, Y, and sample weight. So if you don't specify anything, your sample weight will be none. Otherwise, if you want to balance it out, like something will have some weightage and all of that. So if you can do that. Otherwise, just you need to put the values of X and Y. So what will I pass? This is what I will do. X train, comma, Y underscore train. Model dot fit. Yes, model dot fit is done. And then what will I do? Then model dot predict. Model dot predict of X test, because test has been kept for the testing. So if I run this, it will give me the values, but I want to store it somewhere. So let's store it somewhere. So y pred, let's store the value. So it has been stored here. So what is the data type of y pred? So what is the data type? This is a NumPy array, n dimensional array. Very good. So y pred is equal to this. So out of all the values, this is what we are getting. Okay. Now, the actuals we have, the predictions we have, but we need to calculate the accuracy also, right? So for that, how will I do? So again, I have to, so in the Excel, we were just seeing some R square and those things, right? Some error matrix. Let's import all those things from scikit-learn dot matrix import R2 score. That is one thing we need, and also we need RMSE, root mean squared error. These are the two things that I need. So accuracy is equal to what? R2 score of actual and prediction. So the actual is y test is the actual value, and y pred is the predicted value. So this is my accuracy, right? So I don't need to calculate all the inside things. I will just pass these two arguments into the function I've called, and the function will do the rest of the things. Similarly, the errors. Okay, let's try the accuracy first. How much I'm getting? I'm getting accuracy is only 48%. This is not at all good. This is not at all good. That means my model is not good. I have to rework on the model to improve the accuracy, right? So let's do one thing. Let's simply drop the order quantity for now. Let's consider this one and let's change the state, and rest of the things will remain same. The rest of the things will remain same. No, the accuracy has gone down to 34. So that means this variable was needed. This variable was needed. I should have the order quantity in place, right? So let's do one more thing real quick. Let's see what is your distribution. What is the scatter plot distribution? So how do we do it? SNS dot scatter, SNS dot scatter, and just put, if I put X, see there is hardly any correlation because majority of the data point lies between this. Even though numerically these numbers look good, but visually, there are hardly any correlations between profit and order quantity. So profit and order quantity are not correlated. Very good. Let's see what about profit and sales. Let's see that. X is equal to df dot profit, comma, y is equal to df dot sales. Let's see. Yeah, still okay. It's not very good, but it's still okay. So profit and sales are connected. Let's see if order quantity and sales are connected or not. So order quantity and sales are no, not at all connected. So in that case, what we have to do, there are multiple other techniques that we should try. But on top of it, the point is, this is how you can create a model, even though the model accuracy is less. Even though the model accuracy is less, but this is how traditionally you create a model. Okay, so this is the basics of a linear regression. Now we will go details into it later, but for now, understand just the basics of a linear regression. So tomorrow we can probably take one example and start in details, and we will try to see how good or close we go with respect to predicting some actual values. Right? Hello?
Yeah.
Any questions?
Hello. No, it's fine.
Root mean square error, y test, comma, y pred. So 2892 is the root mean square error. So every time we have to try out various things and we have to see if this one is going up or down, right? So if I change this and if I rerun the whole things, we will see if we are getting 2892 or not. No, 2984, the error percentage is, the error is increasing, which is not really a good model. So though that is how essentially, so we decide whether we should stick to a model or because see, this machine learning models, this is not a one-step solution. One-step things are your steps. You should know what are the sequence you should have in your model. First, do the EDA, understand each and every variable, select the only important ones. That is also something that we will cover tomorrow. Let me just write it down so I'll remember. Feature selection, feature elimination. We will explore this part tomorrow. So what a feature means, the column. So which are the columns we should have, which are the columns we don't need, and we should drop. So that is a very important thing. So once that part is done, then we will just do a trend test split and then the essential models. Now, imagine doing this in Excel. It will take a lot of things to do. But in Python, it's just couple of lines of codes and that's it. You're ready. So, which is the best one. So Python will directly give you which line is the best. So if you remember, Sian, we were just seeing there are multiple lines, right? You change the coefficient and slope, the line will change. We don't need to do all of that here. In Scikit-learn will by default give you the baseline. So that's few of the things on linear regression. And similarly, there is something called logistic regression that is used for classification that we will cover later. But tomorrow, let's plan this. I will take one data or I will take an existing code, a lot of so, and these are few of the things that we will see if it's working or not. The feature selection, elimination, selecting the model. Now that you know about the Python details, you'll be able to follow the steps. It will not be alien to you, right? And this root mean square error, you just go to the other video yesterday. There I have explained how this root mean square error is calculated, how this R2 score is calculated and all of that. So that has been already explained.